All right, so we talked about all the rules for oxidation numbers, and I'm going to pick up with some examples here. After I get through the examples, then I'm going to try to do the thing on the board again to show you a couple of the redox equations. In looking at the first couple of examples here, the concept is they are pure elements. If you have a single atom of phosphorus, it doesn't have to be a P4 molecule. As long as it is a unionized atom of an element, your oxidation number is assumed to be 0. All of your protons are canceled out by matching numbers of electrons. Back to maybe there's a subscript. I picked on a different different diatomic for the next one. Hydrogen being one of those that likes to occur in pairs. Doesn't matter that there's 2 of them, because there's no other element present that's going to give you a 0 oxidation number. How about carbon monoxide? Capital C, capital O, it's not cobalt. The best way to do these is a little bit like we started in the nomenclature end of things, is start at the right-hand end of the molecule and work your way backwards. So using the oxygen rule, and this is not a peroxide, we are then assuming that the oxygen is a relatively normal -2. Because this is a non-metal only molecule, your carbon has what may be viewed as a non-traditional charge. When we were just putting it into periodic table information, we kind of said, here's the most common charges, and we went 1, 2, 3, 4, 3, 2, 1, 0 as we went across the table, skipping all the transition metals. If you have 2 nonmetals stuck together in a molecule, generally speaking, the first one is assumed to be positive. That's one of the things we said when we were doing the nomenclature part. But you can also kind of make the assumption that the first one is often not the charge that you might expect. Carbon tends to be ±4 most of the time. But when you stick it to another nonmetal, it can be something different. So in this case, it's +2. Because CO is a neutral molecule, we want to do that whole thing where everything cancels out again. Hydroiodic acid, HI, that kind of goes back to the same charges that we were looking at in nomenclature. Your hydrogens, it's normal +1 because it's not stuck to a metal. Iodide is its normal -1. And then I picked on 2 related molecules, one of which is neutral, but the other one isn't. So SO3, this is not sulfite. This is sulfur trioxide because there is no charge on it. The goal here is that I want to have all my negatives cancel out all my positives. Again, start kind of at the right-hand end and work your way backwards. If my oxygens are -2, and there are 3 of them, that end of the molecule is worth -6, which then makes the positive end need to be +6. Again, we're hitting that idea where the front non-metal has a kind of unusual charge. Normally, we're kind of used to seeing sulfurs as -2s. Here, because it's part of a totally non-metal molecule, it's +6. But then we look at sulfate. Now, this one is not a neutral substance. It's a polyatomic ion. We have 4 oxygens. Each of them is -2, so that's 8 negatives. I want 2 of them to not be canceled out. So my sulfur is +6 again, but note that doesn't match. I have 8 negatives and 6 positives, This is actually the Y behind the sulfate having a negative charge. Because back when we started nomenclature, we went, just take it on faith, just believe it the way it is. Now we kind of get to, there is actually a reason. It has to do with the oxidation numbers that are created on the front nonmetal. But not all of them are non-neutral. Most of them tend to be neutral if you're talking about polyatomics. I picked two more molecules that have a lot of nonmetals involved here. N2O5. Start with your oxygen. Each of those is -2. There are 5 of them. But note, there are 2 atoms of nitrogen. I need to divide that +10 in half so that each one of those atoms has an identical charge, and they will each end up being +5. Similarly, with my PF3, start with your fluorine. Fluorines are -1s. I got 3 of them, so that half of my molecule needs to be -3. My phosphorus, instead of being a somewhat typical -3 because it's in the same column as nitrogen, is actually a +3 in order to make this be a neutral molecule. So now we begin to look at reactions. Okay, and I'm gonna do a couple of these on the board, so I'm gonna unplug my laptop and see if I can carry this over here and have it work. Never make the bottom part of the stand spread out. Is that right side up?
Yep.
Okay, let me do the stop share thing. You can see I have algebra all over the board because I was doing algebra problems with my daughter this afternoon. All right, so let me talk about redox equations for a couple of minutes before we switch over to stoichiometry. Here's an equation, and these are the ones that are actually in your notes. I'm just doing them on the board so you can see me draw arrows and stuff. 2 copper atoms, molecule of oxygen, 2 CuOs. In order to figure out what got oxidized and what got reduced, I need to go through and label all of them. Pure metal, so this one has a 0. Pure oxygen, yeah, it's a diatomic, but it's still pure oxygen. So that one's 0. Then I go over to the other side, and we've got a -2 and a +2, because this one is a neutral molecule, so I want to make sure they match. All right. Connect them in the direction of the arrow, and look at what has happened to them. Copper started out as a 0, and it went up to +2. So this is telling me that I have an oxidation occurring. Copper got oxidized. It lost electrons. My oxygen started out at 0, but it went down to -2, so it got reduced. You always have to have a pair, okay? The electrons have to go somewhere, so if you start out with one thing being oxidized, at least one thing has to get reduced.
You could have more than one, but typically you have a minimum of one of each thing. What if you have some non-metals? I'm going to pick on nitrogen gas and 3 hydrogens. And this is going to make 2 ammonia molecules. Ammonia is weird. Ammonia is atypically backwards, in part because it's a molecule that we've known about the existence of for hundreds of years, so it kind of doesn't follow the rules exactly. Nitrogen is pure here, so it's 0. Hydrogen is pure here, so it's also 0. Here's where we get to the backwards part. It's not stuck to a metal, okay? Your hydrogen is actually stuck to another non-metal, so hydrogen is its normal +1. My nitrogen is its normal -3. So this gets back to looking at what's happening as you're going from left to right. My nitrogen went down. I went from 0 down to -3. So this is going to be reduced. On the other hand, just like the one above there, as I kind of draw in between here, I went from 0 up to +1. So my oxidation occurred to my hydrogen. There are some things you can kind of make predictions about. I won't call them rules because there are no absolutes, there are some variations. But it is typical for a metal to be the one that got oxidized and the non-metal to be reduced if you have one of each. In this case, we had 2 non-metals. I very definitely have to look at the charges in order to help me figure out what happened to each one. What if you have metals that are combined? Okay, not to each other, okay, but you have 2 metals that are actually part of the same reaction. These are also sometimes referred to, your textbook doesn't really call them this per se, but they're known as single replacement reactions. Magnesium and silver nitrate does, oops, no, I forgot my coefficient. This is actually supposed to be +2 silvers. Gives me magnesium nitrate and 2 silvers. All right, back to looking at what are my oxidation numbers. 0 for the pure magnesium, but also 0 for my pure silver. Because the nitrate is the same thing, okay, they don't actually usually apply this word to redox stuff, but truly it is a spectator. It didn't do anything. It started out life as a nitrate, it stayed a nitrate, nothing happened. I can treat the nitrate as a -1, which makes my silver +1 in that molecule. It also makes my magnesium +2. Sometimes you have elements that did nothing. The nitrogen did nothing, the oxygen did nothing, they just hung out and swam around in the solution. If I look at my changes though, my magnesium went up from 0 to +2. So it's the one that got oxidized. My silver is the one that got reduced. It started out life as a +1, and it turned into a 0 as it went through the reaction. So it is your reduction. Remember I said you gotta have at least one of each, but yeah, sometimes you have ones that actually don't do anything. We need a couple more terms here. In addition to the terms oxidation or oxidized and reduced, we also need agents. All right, so if you have an oxidizing agent, Okay, think of it like tickets. Okay, granted, nobody's going to concerts right now, but we all kind of know the idea. If you're going to the amphitheater to go see somebody perform, you don't actually buy the ticket from the band. Usually you buy it from like Live Nation or Ticketmaster or some similar company that does that. They are a ticketing agent. They do something either for or to somebody else. So an oxidizing agent gets reduced and oxidizes something else. It's doing the oxidation to another substance. And since everything in redox is paired, we also need a reducing agent, so it kind of does the flip. A reducing agent gets oxidized, and it reduces something else. So the idea here being that something got oxidized, something got reduced, and in concert with that then, something is an oxidizing agent and something is a reducing agent. So let's see, which is the one that I picked on for this one? Oh, potassium and chlorine. All right, metal, non-metal, fairly typical in the way they perform. We've got, let me just put a hash through it, a 0 for the potassium, a 0 for the chlorine, +1 and -1. So we're going to do potassium started out as 0, turned into +1, so it's the oxidized one. Chlorine started out as 0, it went down to -1, so it is reduced. You can then also say that since potassium was oxidized, it is the reducing agent. Chlorine got reduced, it is the oxidizing agent. Now think about this for a moment, okay? You want to turn your clothes white, you want to use probably bleach, okay? Bleach also sometimes gets referred to as chlorine bleach. Chlorine is very typically an oxidizing agent. It got reduced. It went from 0 to -1. It stole electrons from somebody else. In the case of bleaching your clothes, it steals electrons from the molecules that have pigment or are stains. Okay, so there's really some truly real world applications to why this works the way it does. I have a couple more molecules to talk about. Again, these are in your notes. Couple of messier looking molecules. How about PF6 minus? I want to figure out what the oxidation numbers are for these individual elements. Start on the right hand side. F's are -1s, so all of those are -1s. I want to have one of those negatives left over. One of them should not get canceled out. In order to make that happen, I need to make my phosphorus be +5. 5 negatives, or 5 positives, 6 negatives, which means I have a misbalance or an unbalance. So that 1 negative is why this really odd, not neutral molecule actually has charge for it. H2ASO4. This is one that you kind of have to do from the outside edges toward the middle. take a look at your oxygens. I mean, we're going to kind of write these out. We've got 4 of them, so 4 -2s. Hydrogen is kind of normal here. It's not part of our hydride or anything, so it's +1 and +1. That means I need to kind of figure out what's left over. 8 negatives, 2 positives already cancel some of it out, but in order to make this kind of turn out the way I want it to, this means that I need to make my arsenic. Actually, I just realized I have a glitch in my notes. It's supposed to be +5. Because we have to have 7 positives, so 1, 2, and 5 makes 7. And 8 negatives, so you have 1 negative left over. And yeah, actually, in looking at my notes, I have arsenic labeled as a +7, which is wrong. It's actually supposed to be +5. Things that happen when I type.
Would that be +6?
No, because I don't want all of them to cancel out. I want to have 1 negative.
Oh, right,
left
yeah.
over.
I got it, yeah.
One of them should be
right.
remaining.
Mm-hmm.
Here's a uranium-containing little molecule. Got a +2, so if oxygen is -2, in order to have 2 positives, I have to have more on my uranium. And again, I think I copied some notes from one place to another place, and this is supposed to be, okay, I know what I did. I forgot my subscript. Because this is, okay, if you actually look in your lab book, there are 3 positive polyatomics. The one we see all the time, which is ammonium, NH4+, and then there's 2 bizarre ones. This one is called uranyl because it has uranium in it. And I forgot to include my subscript when I typed it. Like I said, I'm kind of looking at my notes. I don't think I corrected it when I posted them. So yeah, I kind of glitched. This is supposed to be UO2 because that makes your uranium +6 and 2 -2s for your oxygen, and that way you have two leftovers there. So yeah, I have a couple of glitches. It's like I said, I'm so used to doing this stuff on the board that when the notes are usually just sort of a prompt for me so that I don't forget to do things, and I don't always double check the stuff when I'm typing. So yeah, there's a couple of glitches on this. I have one last very messy looking reaction that I want to show you. This one involves iron sulfide and 3 nitrates, 4 hydrogens, and I'm going to kind of draw my arrow there. And it gives you 3 NOs and a sulfate, SO4 - 2, and iron +3, and 2 water molecules. This one is messy. It's got lots of elements. Bare minimum, at least one thing has to get oxidized. At least one thing has to get reduced. In this case, we actually have 2 oxidized and 1 reduced. So I'm going to go through and I'm going to label them. My sulfur is -2, which makes this iron +2. This time I can't assume that my nitrogens and my oxygens are just like spectators alone because they changed. But all of my oxygens are -2s. My nitrogens aren't. This nitrogen has to be +5 because I need to have 1 negative left over. This nitrogen needs to be +2. I'm looking at making sure I didn't totally glitch out this one either. Sulfate we already did. So sulfates are -2s and +6. This one's just +1 because it's a single hydrogen ion. This one is +3 because that's what the charge is on my ion, my oxygens, and my hydrogens. Now everything's labeled. There are elements that didn't do anything. Nothing happened to hydrogen. All the hydrogens here are +1. All the hydrogens there are +1. They didn't do anything. Oxygens were -2. They're -2 here, they're -2 there, they're -2 there. Oxygens just swam around and did nothing. But my iron changed. It went up. It went from +2 up to +3. But it's not the only thing that changed. Also, my nitrogen, +5 to +2. That changed also. It got reduced. That also then leaves me sulfur that I didn't touch yet. It went up a huge amount. It went up from -2 all the way to +6. One of the reasons I wanted to go through this one is it was an example that gives you 2 oxidized elements and 1 reduced element. Now, if you actually go on to take second semester, one of the things that we'll talk about is keeping track of how many electrons you're trading. This semester, we just want to know what got oxidized and what got reduced. We're actually not balancing the redox equations in acid or in base, which is a facet of dealing with it during second semester. So this is kind of a one-phase sort of thing. It does get into a deeper version of it if you take the second semester. I think that gets me all the way through the end of redox. So I'm going to try to unplug my camera here and go back to desk. Let's see if I can convince my webcam to behave. That more or less works. All right, we are about 3/4 of the way through the chapter now. The last big segment of this chapter has to do with stoichiometry. So let me see if I can show you my picture. All right. This is sometimes referred to as the stoichiometry roadmap. See where it says given. Typical stoichiometry problems that go through all the steps start with one of 3 items. Most of the time it's grams, but you also might see liters if we're talking about gases, and or you might see particles, something to a high exponent. Note, everything has to pass through the bottleneck. Everything that came in and turns into moles of X, they're calling it, has to go 2 moles of Y before you get out the other side. And again, most of the time, we are looking at masses as your find, or that's what your answer is supposed to be given in. But we will also do a little bit of volumes or
particles. I pulled this just off a website. I think there is a version of this roadmap in your textbook, but I'm not sure what page it's on. You can always Google for it. It's kind of a helpful idea as just kind of giving you some, where am I going information that you have to go through a set of steps to make this work. All right, let me switch to a different document then. Back over to the notes thing. All right. We've been doing grams and moles and sometimes molecules. We've also done some balancing. Stoichiometry is synthesis. Stoichiometry is pulling a whole bunch of different pieces together to do entire calculations. Let me pick on one that we used when we were balancing. Take a piece of magnesium, drop it in some hydrochloric acid. There's a 2-to-1 ratio. You get some magnesium chloride, you get some hydrogen gas. We're actually going to kind of start in the middle of the roadmap. The roadmap, probably the key function, is all about the ratios. My magnesium hydrochloric acid reaction is a 2-to-1 ratio. I need twice as many HCl's as I need magnesium in order to get this to work. And so I picked a random number. Let's start with 0.28 moles, kind of a not nice round number exactly. How much HCl would you need to go with it? Set it up so that it looks like a fraction. It still obeys the rules of math in that the thing you are looking for goes on the top, and the thing that you want to cancel out must go on the bottom. So I have 2 HCl's over 1 mg, which basically means I need to multiply my 0.28 times 2, because dividing by 1 doesn't change anything. I need 0.56 moles of HCl. Straight up 2-to-1 ratio. Sometimes the thing that you are looking for is a product and not another reactant. So I picked on another different reaction here, one that didn't have any ones. 2 potassium chlorates, 2 KClO3s, make, after you cook it, 2 potassium chlorides and 3 oxygens. If I want to find out how much of each product I get, note I got 2 different products, so I'm going to have 2 different answers. I'm also going to have 2 different little fractions in order to do my conversions. Take the number that you are given, 0.7 moles. For the first one, it gets multiplied by 2 over 2. 2 KCl's over 2 KClO3s. Obviously, that doesn't change your number. It does change your identity because the KClO3s will cancel out. One is on the top and one is on the bottom. If I look at the second product, start with the same information again, 7/10 KClO3, multiply it by 3 O2s over the same thing, 2 KClO3s. Different number this time as well as different thing. 1.05 moles of oxygen. If you have 2 different products, you're going to have to do 2 different steps for your math. Here's another one that has slightly bigger numbers. Propane. Yes, this is the stuff you put in your gas grill. C3H8. As opposed to the stuff that comes through our Bunsen burners in lab, which is methane, which is 1 carbon and 4 hydrogens. You need oxygen to make something burn. This is a combustion reaction. You get carbon dioxide and water. I decided to start with 4.3 moles of propane. I want to know how many moles of carbon dioxide and how many moles of water I'm going to get. The same method is used here. Take your initial value, 4.3. The first fraction has a 3 on the top and 1 propane on the bottom. Multiply your 4.3 times 3, you get 12.9 moles of CO2. For your second step, the propane still stays on the bottom with its coefficient of 1, because remember the 1s are implied even though they're not written. 4.3 times 4 will give you the 17.2 of the water. So this first set of information is giving you the middle step. Basically, it's the moles of X to moles of Y step. That's the middle of the stoichiometry roadmap. Now we need to back up a little bit. Now we need to tie the grams into it. Like I said, grams is probably the most often used, and it's actually what we are going to use when we do the limiting reactant lab that is upcoming. I started with a nice 1-1-1 equation. 1 calcium carbonate, you heat it, it decomposes, you get 2 products, you get 1 molecule of calcium oxide and 1 molecule of carbon dioxide. So this one's kind of straightforward on the coefficient end of things. I did this one first because not having to deal with both at the same time when you're first starting it out is probably a good idea. If I have 15 grams of the calcium carbonate, this is a 3-step calculation. The first step is your take the grams, turn it into moles step. Typically, this is a division step because you need to divide by your molar mass. This is also why we did molar masses in the previous chapter, because they come back again in this chapter with a different use. 1 calcium, 1 carbon, and 3 oxygens has a molar mass of 100.1. So I do my division, and I get 0.15 moles. Then I do my ratio step. And this one's a little bit kind of duh, because it's 1 and 1, but I did it because it shows you how things to cancel out. 0.15 of the calcium carbonate times 1 calcium oxide over 1 calcium carbonate. Your CaCO3s cancel out. Your number doesn't change, but the what it is changes. Now I've got 0.15 moles of calcium oxide. Your third step, I need to turn it from moles into something more measurable, which in this case is grams. 1 calcium and 1 oxygen have a molar mass of 56. Multiply those 2 numbers together, and you get a yield of 8.4 grams for your calcium oxide. You could tie these three steps together. It does not have to be done in 3 separate steps. In fact, I think some of the examples that are given by the textbook actually break it into, or actually don't break it into 3 steps. I believe some of the examples tie it all together and kind of string it all together like a multi-step dimensional analysis. it can be done either way. It doesn't affect the math. You can do it as 3 individual steps, or you can do it as 3 continuously linked steps. It doesn't change your answer. All right, let's look at another combustion reaction. C2H2 is known as acetylene, the stuff that they put in blowtorches. It is a combustion reaction. You need oxygen to make it burn. You get kind of the same sorts of things that you get from when you burn the propane. You get carbon dioxide and water. The biggest differences are all my coefficients are different. I've got 2 acetylenes and 5 oxygens. And it gives me 4 CO2s and 2 waters. This time I want to know how many grams of oxygen I'm dealing with. So in this case, I'm going to start with my 40 grams. C2H2 has a weight of 26. So do your division step. I get 1.54 moles. Now I have a not 1-to-1 ratio. I have a 5-to-2 ratio. 5 oxygens for every 2 acetylenes. Do that math. Multiply by 5, divided by 2. You get 3.8 moles. I want grams. So my final step is multiply your 3.85 moles times your 32 grams per mole. Moles cancel out. You get 123 grams. I could have actually done this in liters. The third step would have been different. Later we'll circle back around to this, but the magic number that when it applies to gases is 22.4. That's a number you'll hear again later. All of these have been kind of focusing on the idea that you know one thing and you are calculating the rest of it. It's actually not the way real reactions work, typically. Usually you want to figure out what would be the magic ratio if everything got used up and you had no leftovers. All right, so I subscribe to Oberweis, the people who deliver your milk, but they also deliver eggs. We got our delivery morning is Thursday, so we got milk and eggs this morning in the cooler. We now have like 14 eggs in the fridge. Well, if I was going to go make a cake, and my cake recipe says I have 4 eggs per recipe, well, obviously I have more eggs than I need. Okay, I'd have leftovers. I wouldn't be using them all. But then maybe I didn't have a lot of flour left in the container. Maybe I only had a couple of cups of flour left. So maybe I'm going to run out of flour before I ever run out of eggs in terms of making a cake. So more buzzwords here. Limiting reactant. It's the one you run out of. The lab that we are going to be doing in a few weeks has 2 separate reactants, and every student is going to be issued 2 amounts to use, one for reactant 1 and one for reactant 2, and you're going to calculate which one you run out of mathematically, and then we're going to do it for real, and you're going to do some tests that prove which one you run out of. So limiting reactant is the one you run out of. Excess reactant is the one you had left over. And I picked on a pretty straightforward little reaction here, sodium and bromine. 2 sodiums to 1 bromine. Note the bromine's a diatomic molecule. And it gives me 2 sodium bromides. What if I started with 5 of each? What if I gave you 5 grams of sodium and 5 grams of bromine? Sodium and bromine don't have the same atomic mass. They have different masses on the periodic table. So I did this as two separate steps here. You're doing the same steps. You're just doing the same steps more than one time. 5 grams of sodium. Sodium weighs 22.99 on the table. I have 0.22 moles of it. 5 grams of bromine. Bromine weighs more. Even one bromine weighs 79. 2 of them weigh 159.8. I have 0.031 moles. I need to test it because this is not a 1-to-1 ratio. I need to test it to make sure which one I think I'm going to run out of. Typically speaking, most of the time, you should test the smaller number. About 80% of the time, it will be the one that you run out of. Not always. Kind of like when we talked about precipitation reactions, there are some cases where the other thing is true. When we did precipitation reactions earlier in the chapter, we said sometimes there is no precipitate. In this case, for stoichiometry, sometimes, like maybe 15, 20% of the time, the small one is not the one you run out of, but you need to test it. There are other methods to do this. This is the way I like to kind of teach it. There are other ways to do this. So I picked the small one, and then I did my ratio, my 2-to-1 ratio. If I use every molecule of my bromine, I need 0.062 moles of my sodium. And I'm in luck. I have lots more sodium than I need. I have 0.22 moles of it. I need about a quarter of that, 0.062 moles. And yes, I'm in luck. The amount that I needed is less than the amount I have, so my guess was correct. Once you figure out which one is limiting, this then determines how much product you can make. And it kind of goes the same way. Start with the thing you know. In this case, start with the limiting one. I have another ratio involved here. Like I said, you're doing the same steps. You're just doing some of the same steps more than one time. The ratio this time around has NABR on the top. So 2 sodium bromides per 1 bromine molecule. The number of moles is the same, 0.062, but this time it's moles of sodium bromide. And I got one more step. This is one that wants me to find it in grams. So I got to go back to grams again. I need a molar mass. Sodium bromide has a molar mass of 102.89. Do that final multiplication step. And even though I started out with 10 grams of stuff, 5 of bromine and 5 of sodium, I don't get 10 grams of product because they didn't match. I only get 6.38 grams of sodium bromide. We're going to call this the theoretical yield. Theoretical yield makes an assumption which is seldom true. Theoretical yield is kind of this idea of everything worked exactly the way it was supposed to, and everything got used up, and nothing got stuck to the bowl, and everything. It's the perfect scenario. Actual yield is real life. Percent yield is the ratio. Percent yield is actual over theoretical. And because it's a percent, we got to multiply by 100. So because I am evil, when my son took chemistry from me as a high school student, we did limiting reactants and theoretical yields and actual yields making muffins. First, we calculated what our theoretical yield was based upon the recipe. Then we actually made muffins. And actual is never quite what you expect. You know how you read the recipe and it goes, makes 16 muffins. And of course, this presumes that like nothing got stuck to the inside of the bowl and every muffin was the exact same size and things that don't really happen well in reality. And so we made the muffins and came up with a number and compared actual to theoretical and did a percent yield. So there are real world applications for this. And I have one last kind of messy looking equation here, messy looking problem. Iron oxide, also known as hematite, and carbon monoxide. If you stick the two of them together, you get iron as a pure element, but you also get some carbon dioxide. So we're going to start with two differing amounts. We want to find the limiting one. We want to find out theoretical yield, that's the how much would be produced. I gave you an actual yield, but I also want to find out how much is left over of the one that I didn't run out of. This is very similar in a lot of ways to the math that will be applied to the lab that we're doing. 40 grams, iron oxide, has a mass of 159.7. So I've got a quarter of a mole of my iron oxide. I have 15 grams of carbon monoxide, but carbon monoxide weighs less on the molar mass end of things. It only weighs 28. I have a little over half a mole. So I'm going to make an assumption, which doesn't turn out to be true. I'm going to assume to start this problem that I'm going to run out of the iron oxide before I run out of the carbon monoxide. I took my number of moles, I did my 3-to-1 ratio, make sure you are using the balanced reaction numbers. And it says, oh, I need 0.75 moles of carbon dioxide to go with this. Well, okay, that doesn't work. I don't have that much. I only have a little over half a mole, 0.536. My guess was wrong. And since it's only an either or option, if it's not one, it has to be the other one. Yeah, there are reactions in real life that have more than 2 molecules involved, but for general chem purposes, we don't usually deal with that. It's actually my carbon monoxide that's my limiting reactant. Now I'm going to use the carbon monoxide to help me figure out how much iron I would get. So I've got a different ratio this time. This time it's 2 irons to 3 COs. I get 0.3573 moles. And then I need grams. So multiply by 55.85 because that's the number from the periodic table for iron. So if everything had gone pristinely perfect, I would have gotten slightly less than 20 grams, 19.955. I'm going to digress for a moment here. Since my carbon monoxide was my limiting, that means my iron oxide was my excess. How much didn't get used? Well, back to ratios again. I have a 1-to-3 ratio. I used up 0.1787 of my iron. I had a quarter of a mole to start with. So I subtract. I had 0.0713 moles left. Multiply that times its molar mass. Of my original 40 grams that I started with, a bit over 11 of them never got used. They just kind of ended up in the bottom of the bowl. But it also asked me to find percent yield. It said, somebody did this for real. They got 17.64 grams which needs to be divided by the perfect number there of 19.995. And that gave me an 88.22% yield. Not awful, not amazing. Some things didn't work out well because I had a lot of leftovers that never got used. So all of these pieces kind of pull together. The idea that kind of goes behind the stoichiometry is you're always trying to match stuff up. How much did you start with? How much did you use? How much could you have made versus maybe how much happened in reality? Textbook problems give you usually data that's a little better than average, but not always. Sometimes they purposely make the data a little bit messy. Let me talk about homework for a minute. Let me twist around and grab my homework off the floor. I'm trying to make sure if I've grabbed the right pages or not. All right, I think I did all of these. So this is the end of this problem, at the end of this chapter. There are a mixture of things that are all covered in this chapter. When you pull up the homework set, actually, maybe I should pull up the homework set so we can have a look at it. Where's my... And I put that in the wrong place. I put it in the wrong folder. There, okay. All right, this is what your homework looks like. So it starts with balancing reactions. Remember that you are shooting for whole numbers, mostly small whole numbers. Then we move on to solubility. Make sure you are using your solubility rules to help you with this. Then we move on to precipitation. And number 6 is designed to kind of help you along a piece at a time. This is why it has an A and a B and a C and a D, is it's supposed to kind of help you learn the process that you're going through as you're doing these kind of reactions. And then for number 7, I didn't lead you through it. Then we switched over to acid base. There's a gas generating reaction for number 9. Some oxidation states. Make sure that when you are doing the oxidation states that you do the oxidation number for each of the elements. For instance, like HCO3 minus has 3 elements involved. Figure out what got oxidized and what got reduced, and what the oxidizing agent and what the reducing agent are for the iron oxide and the CO. The one we're looking at from a stoichiometry point of view, then we're going to go back and look at it from a redox point of view. And then the next couple here are the first, number 12. Again, I tried to kind of lead you through the process a little bit, asking you things a piece at a time as that is sort of goes through all of those steps. And then there's one that kind of like the last example, kind of gives you everything. And figure out what your limiting reactant is. You don't have to figure out what your theoretical yield is for 14, just which one is limiting. And then there's another one that kind of pulls all the pieces together again for number 15. So all of this is a mixture of things that we covered in this chapter. This makes homework then due on Tuesday before midnight, so I can then have a couple of days to grade it. If homework is due Tuesday and I go over it on Thursday, it probably means that the test will be not this weekend, but next weekend. So about a week and a third, a week and a half from now, and I'll probably give you the 4-day window again. It works better if I schedule tests from Friday to Monday, as opposed to trying to do it in sort of like the middle of the week. The only time we hit middle of the week problem is right at the very end of the semester. But as we're progressing through the semester, I usually try to make it match up so that the tests fall where you have a number of days to choose from for working on your test. Questions about this chapter? Probably you may not end up with questions until you actually dig into the homework. I will have access to email tomorrow night when I get up past DC, and I'll definitely check my work email or my other email too. But I won't be home and have easy email access until Saturday night. So if I'm slow to respond to questions you have regarding homework, this is why. Questions? All right, so dig into your homework, and I will see you I see some of you on Monday, and everybody else on Tuesday then.
Have a good weekend.
Thank you.
Have a good weekend.